Now let's discuss the proton-proton chain. This is the fusion process that produces over 85% of all the energy that the sun radiates away. The remaining 15%, that's through other fusion chains involving things like this heavy hydrogen or even helium bonding with other protons out there. But the vast majority of the sun's energy falls into these three-step process. You notice here's step 1, here's step 2, and here is step 3. This is a separate chain that will go together into the final step 3. So there's a lot of information here, and I want to break it down step by step over the next couple of slides, and we'll build up our terms and what all is happening in this complex figure. So we'll go to the very first step, and you're going to have 2 protons. Right? Another way of saying 2 hydrogen atoms. Hydrogen by itself is just a proton. So you have 2 protons, and they're going to fuse together in a collision event, and the output will be this deuterium. It's also known as heavy hydrogen. Remember that the chemical element, what defines what element you have, is the number of protons you have, red being our protons. Whereas the gray represents our neutrons, which have no net charge. So while this whole thing has an atomic weight of basically 2, its chemical element is still hydrogen, 1 proton. So this is one of the outputs of this collision, but there are 2 others that matter. One of them is the neutrino. Now we're going to have an entire separate section of videos dedicated to just discussing this neutrino. For now, I'll tell you that this guy, this little neutrino, gets to fly straight out of the sun, go off into space. Whereas the other thing that gets produced is this tiny positively charged particle that we call a positron. A positron is, for another term, the anti-electron. It has the same mass, but just same mass as an electron, but the opposite charge, making it positive. So I'm going to use the phrases positron or anti-electron interchangeably because they represent the exact same physical thing. So recapping this, 2 protons smashed together. The things that fly out of that is a neutrino, a heavy hydrogen, and a positron. Positron being antimatter, this thing, while free away from this fusion chain, will eventually interact with an electron. They're oppositely charged objects. They're naturally going to be attracted to each other. And when the matter-antimatter react, they annihilate, completely destroying each other. All the energy from this electron and this positron's mass gets obliterated and converted into high energy photons. Specifically, 2 photons are radiated away. So reading this off, kind of like a chemical equation, you'll start off with 2 separate hydrogen protons. They'll fuse together, turn into deuterium plus a positron. E plus is positron. That positron will then later interact with another electron. They'll annihilate. So positron, E plus, adds to a electron, E minus, and they will annihilate each other into 2 photons flying away. Whenever we see photons leaving, that's energy exiting the sun. Mass from these protons are getting converted into energy that leaves the system. Same goes for this neutrino, but we're going to table conversation on this neutrino for later. Leading into our next step, this deuterium, here it is again, our deuterium will collide with a proton. That fusion process will generate a photon, energy flying away, plus a helium-3 atom. Helium, 2 protons, so this is chemically helium, but it's got only 1 neutron. This is not a stable nucleus. This thing, left to its own devices, will eventually just decay away. So this is a short-lived process, but luckily there is an insane amount of these things nearby in the core of the sun. So these things have a high probability of interacting with another helium-3 atom. So reading this off chemically, a heavy hydrogen, deuterium, will collide with another hydrogen atom, or proton. Same names here. So we'll go back again. Deuterium will interact with hydrogen. They'll fuse together, producing helium-3 plus a photon. Helium-3 being a isotope, an unstable isotope of helium. And once again, whenever a photon leaves, that's energy for us to gobble up. Finally, this helium-3 nucleus will interact with another one. And that will be step 3. We'll take 2 helium-3 nucleuses and smash them together. Count up the number of components. 1, 2, 3, 4, 5, 6. When they smash together, no energy is released. A proton fly away, they're liberated, and we have left a chemically helium, but it's helium-4, 2 protons, 2 neutrons. And this is a stable helium atom. So reading that off chemically again, a helium-3 plus a helium-3 collide, fuse together into a nice stable helium-4 atom plus 2 protons that just fly off. They'll be consumed in later nuclear reaction or nuclear fusions. So no energy gets released at this stage. This is just going from unstable helium-3 isotope to a stable helium-4 element. And I'll go back to the big picture. Once again, step 1, energy gets released. Energy gets released as a neutrino and as a positron that will later annihilate with an electron, producing 2 photons. This one up here is the exact same chain, and we just need that secondary chain so that we have helium-3 for step 3. Right, so step 1 terminates into this deuterium. Deuterium will hit with a proton. That proton will spit out energy and leave us with helium-3. Here it is again for our second helium-3 atom. Now that we have 2 helium-3 atoms, those will collide. They'll eject out 2 protons, and we're left with a nice stable helium. And this is the primary source of energy in our sun. These photons and the neutrino, that's the power that we get. So as this fusion process is occurring, there's a lot of these high energy photons that need to leave the sun. So what we're talking about now is how the energy transfers out. Only fusion's happening here in the core. Once you get out of the core, it's just high energy photons that need to go through the radiative zone. And that's what this picture is trying to represent here. If you've ever been to, say, a concert or some kind of a stadium event, inevitably someone has some inflatable ball that just starts bouncing around the event. And you'll notice that the ball has a random, seemingly chaotic pattern, but it inevitably does go one direction. It inevitably does, let's say, for my inflatable ball example, it will travel towards the front of the stage, towards the stadium. So even though the path of the ball is random and chaotic, it does end up traveling outwards. And that's what's happening to the photons. The photons produce in the core into the radiative zone, and they'll interact with matter. Remember, matter loves gobbling up photons, get those electrons into excited states, then emit them out in a random direction. So photons traveling, gobbled up, then spit out in a random direction. Bam. Gobbled up, spit out in a random direction. Gobbled, spit, gobble, spit, go forth. So the photons produced in the core of the sun have a very long, slow process to get out there. Once those photons get past the radiative zone, they'll finally enter the convection zone. And there what is happening is that these gases are getting heated up from the energy deep down in the core. So this energy is doing its random sporadic pattern, and then it reaches the convection zone where you heat up the gas, that hot air can rise up, release their energy, warming the environment around them, and fall back down. Remember that. The hot air rises, the cool air is falling. So altogether, a photon that's produced deep down in the core of the sun from that proton-proton chain, that photon itself, the energy release in that event, will take 10 to the fifth, about 100,000 years to reach the outer layers of the sun. The light that we see today, that energy, that was produced almost 100,000 years ago.